Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and here's the problem that I posed for you last time. Hopefully you solved this. If not, you have another chance now. Anyway, you know what to do. Let's see how you did. Let's distinguish between going up and going down because they're different. If we look at a free body diagram, we're looking at the forces going up, and we do have to choose a coordinate system, and the coordinate system I'm choosing is down is positive and up is negative. It could be the other way about, and as long as you're consistent, you will get a consistent answer that can be interpreted. But this is up and this is down. So when we're going up, so we're moving, this is the motion, but gravity is retarding us, so mg is going the other way, and also the air resistance is also pushing us down. So you see the SIGN on the force of gravity and the force of acceleration are the same. So Newton's second law says that the net force is going to be the mass times the acceleration. The acceleration is the derivative of velocity, and so it's going to be the sum of those two. I divide all the way through by m, and m was 50, I think, and so this is what I get. And my initial condition was it was initially thrown up at 10 meters per second, so that is minus 10 according to my convention. And so if you look at this, you can say, oh, this is not linear, there's a v squared there, so this is a non-linear equation that I have to solve here. So this is the equation going up. Now going down, we've reached the apex and now we're coming down. We have the acceleration due to gravity that's happening. That's a force that's acting on this. But as we're going down, the mass is encountering resistance from the air. So this is going to be minus 5 v squared because that is pointing up. So this Newton's law ends up with a different right-hand side. ma is going to be mg minus 5v squared, divide all the way through by m, and there is a value we need to have called t0, which is the apex, or what was the value when it was at its highest height above the ground. So these are the two differential equations we have to solve, this one going up and this one going down. Okay, so what we're going to do is we're going to reorganize that, and basically you can say, oh, we separated variables. We're going to integrate and recognize that this is going to be an arctangent form. And I'm putting my constant over here because eventually I want to solve for v, so I put my constant on this side. Some of you asked questions about that, and I don't think I did a good job of talking about that before, but I'm tending to put the c on the side. So when I solve it, it will be over there. And now I know that the initial velocity was minus 10, so I can substitute that into this. And I can solve for c. And so c is this number. Now, you should remember that there are no ugly numbers, just like there are no ugly babies. This is a fine answer. It's messy, but remember the story I told you at the beginning of this lecture. So I put that in for c, and I have this expression. Now, this is implicit in v, so I want to solve this for v. And so what I'm going to do is I'm going to move this constant to the other side, and then I'm going to take the tangent of both sides. And this is what I get for my explicit expression in v. Again, you should verify all of these calculations. But we need to know, in order to solve the second differential equation, we need to know when is this at its highest point. Whence is the apex? Well, that's going to happen when this is equal to 0, because you see the velocity changes signs. It was negative going up. It's going to be positive coming down, so it's 0 at its crest. So what we can do is we can set v equal to 0, and we can solve this, and we find out that this is what t is. Now there's many values for t, but this is going to be the first positive value of t. N is going to be 0 here. You substitute this in, and you will find out that t is a little less than 1 second. And so that is the apex, and that means our equation going down, this is what we came up with on the earlier page for the differential equation involving v, and this is now my initial condition because the velocity is 0 at the apex. So now we're going to solve this. Again, we solve this by separation of variables. We get t's over here and we get v's over here, and we'll integrate both sides. Now this could have been integrated perhaps with a trig substitution, but I chose to do it by partial fractions because we're going to be doing a lot of this when we get to Laplace transforms, probably more than we're going to be doing the trig substitution in this class. So this is going to be partial fractions that we're doing, and so you want to work through that and check that you can do that. But this is the partial fraction decomposition. You integrate it, and going from here to here, I use the fact that the difference of the logarithms is the logarithm of the quotient. And again, since I'm going to solve for v, I put my constant on this side, and I'll solve for it in a bit. In fact, I'm going to solve for it right now. I find out that c is this number. So then I can plug it in, and this is my implicit function in v, including the constant. Now, I do have to, in solving for v, I have to determine whether this is positive or negative. Now, what I've done here is plotted some slope fields. So since the square root of 98 is almost 10, it's slightly above, it's between minus 10 and 10. And so we know that if the velocity starts out anywhere in this region, and ours does because it's at 0, that's between minus 10 and 10, then the velocity is always less than that. And what that means for us is both this and this are positive, so the quantity and the absolute value is positive. Therefore, we can replace those absolute value bars with just brackets, and we can solve for v. Now, solving for v is some algebra that you really want to probably practice, but this is what you get for v of t. And again, this was going down. So going up, we have this expression. Going down, we have this expression. And if you want to find out when it hits the ground, there's more algebra that you can solve, but I am not doing that algebra right now. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless.